Welcome back. We are in the next lecture of Fundamental of Electronics and we will discuss the amplifier frequency response. So the outline goes like this. We will be discussing the basic concept why the frequency response measurement of amplifier is important and how do the capacitors plays an important role in governing the frequency response. What is the concept of decibel in frequency response measurement, the low frequency and high frequency response of the amplifier. We will talk about the total amplifier frequency response using the summation of low and high frequency counterpart, the frequency response of multi-stage amplifier. So what happened with the single stage as well as when the amplifiers are in the multi-stage, and what is the measurement principle and how do you measure the frequency response of the amplifiers. So let us start the discussion with the fundamental concepts. Amplifiers behave differently when we talk about the low frequency, the mid frequency and the high frequency. We have seen that the coupling and the bypass capacitor appears as virtually short at the mid frequency region. So this was what we discussed in the previous lecture. We have sorted the coupling and the bypass capacitors and then we have done the analysis. Generally at low frequency, the capacitive reactance, that is Xc, it will affect the gain as well as the phase shifting of the frequency response. What is frequency response? It is basically the change in the gain and the phase shift over a range of input frequency. So the frequency that we provide as the input, this is basically sweep frequency response. So we can give the input frequency of our choice depending upon the application, and this will affect the gain as well as the phase shifting, and the measurement principle and the analysis is known as frequency response analysis. So first we see like how the capacitance in the circuit plays an important role in affecting the frequency response. We know that the capacitive reactance is given by 1 by omega c, where omega is 2 pi f, and we say that Xc is equal to 1 by 2 pi fc. So omega is the frequency in radian per second and frequency is in hertz. Now two important capacitor that we have in the amplifier is basically the coupling capacitor and the bypass capacitor. So here we can see the circuit. This circuit is made up of BJT. This circuit is for FET. So two type of amplifier circuit where we have taken the BJT circuit and the FET circuit. The capacitor C1 and C3, these are basically the coupling capacitor. The capacitor C2, which is connected in parallel with the ammeter resistor, is known as the bypass capacitor. So we have discussed this in the previous lectures in very detail. Now, how do these capacitors plays an important role? Because in the previous lecture, we used to sort this capacitor because we were discussing about the mid frequency region. But in this lecture, we will see more detail in the frequency response when we talk about the low frequency, mid frequency and the high frequency, or the total frequency response of the amplifier. So when the frequency is low, so if the frequency is low, then the reactance will be reducing the gain. So if the frequency is low, then the reactance will increase and this will reduce the gain. And it will introduce certain phase shifting because the circuit is leading in nature as a result of presence of the capacitor. When we talk about the bypass capacitor at the low frequency region, the Xc becomes significant because if you see, Xc is inversely proportional to your frequency. So if the frequency falls, it is very, very low, then Xc will be very, very high. So this will become significant. As a result, the emitter or the source is no longer at AC ground. So if you see this capacitor C2, which is forming a capacitive reactance Xc, which is very, very high, then very, very high means the Xc is tending to infinity. When we talk about the infinity, it is the basically concept meaning is it is open circuit. So if it is open circuit, all the current will be flowing through this side and it will not be virtually short, what we used to do in the previous discussions. So this reduce the gain due to the impedance which is formed due to the emitter resistor or the source resistor. Now the impedance in the emitter will be equal to the resistance of the emitter because this Xc value is very high. In case of your FET, the circuit will be same. Only in place of emitter, base and collector, we will have gate, source and the drain. And we will also have there the coupling capacitors and the bypass capacitor. The fundamental principle remains the same. Now in transistor, you have certain internal capacitances. So when the frequency is high, the coupling or the bypass capacitor are basically short, and the internal capacitance, like for example in BJT we talk about the base emitter capacitance or base collector capacitance. In case of FET we talk about the gate source capacitance and the gate drain capacitance. This dominate. So here you can see the circuit. This is basically the BJT circuit and this is the JFET, junction field effect transistor circuit. So these are basically the internal capacitances, base to collector, base to emitter. In case of FET, this is gate to drain and gate to source. So these internal capacitances will be dominating when we talk about the high frequency region. It will reduce the gain and it will introduce the phase shifting as the frequency increases. So when we are studying the frequency which is very high, then what happened is basically the gain will be reduced. So we have talked about the voltage gain AV. So this will be reduced and there will be certain phase shifting. We will see this with respect to circuit. The datasheet of the BJT and FET, if you see it, we talk about the input and the output capacitances and the input and reverse transfer capacitance for the FET. So these will be available in the datasheet. There is one important theorem which is known as the Miller's theorem, and this theorem is given to simplify the high frequency analysis of inverting amplifiers. So when we talk about the amplifiers and we need to study the frequency response, especially in the high frequency region, we need a simplified circuit for that, which the Miller has given. Now let us see the effect of the Miller. This is what you have the amplifier, which is denoted with the voltage gain AV, and the input and output part of the circuit is shown. We need to determine the input capacitance and the output capacitance of these amplifier. So it will be simplified in the form that the Miller input capacitance is given by the product of the base collector capacitance multiplied with the voltage gain plus 1. I am not introduces here the derivation part of this one. You can check it out at the book. We are more interested in the final outcome, and the output capacitance of the Miller is given by CBC, which is base to collector, multiplied with certain gain factor, which is AV plus 1 by AV. AV is the voltage gain. So here you can see it. We can have the simplified circuit of the amplifier with the introduction of the input capacitance and the output capacitance with respect to the Miller effect, which is the internal capacitance multiplied with certain gain factor. So this is with respect to the FETs, the BJTs. If we talk about the FET, we have to replace the base to collector with respect to gate drain capacitance. That's the difference. Otherwise, the circuit remains the same. So here we will see. So this is your BJT circuit and this is your FET circuit. We will introduce the concept of Miller and we will determine the internal and the external, which is input and the output AC equivalent circuit. So we have taken this capacitance, which is CBC AB plus 1. This is our input capacitance with respect to Miller effect. This is the output capacitance CBC multiplied with the gain factor AB plus 1 divided by AB. And in the FET case, instead of having the base to collector, we will have gate to drain multiplied with AB plus 1 and gate to run multiplied with the gain factor AV plus 1 divided by AV. So here we have introduced the Miller capacitance in the input and output of the amplifier circuit. Now, next topic that we take is basically the decibel. So this is the unit which is in logarithmic for basically the gain measurement. So we need to measure the gain. So if we need to measure the gain, we need certain unit, and that unit is in decibel, which is basically logarithmic. So let us see the power gain and the voltage gain. So these are two important gains that we talk in amplifier. One is the power gain and second is the voltage gain. So power gain is basically denoted with AP, voltage gain is denoted with AV, unit is in dB, which is decibel. So this is equal to 10 logarithmic of AP. So this is natural logarithmic, and this is the power gain and the voltage gain. So here you have basically 20 log of AV. So the voltage gain or the power gain, if it is positive, gain is positive, we talk about the positive dB. But if the gain is negative, it means the attenuation is there and you have the negative dB of the circuit. Okay, so that is what you have. Now, when we talk about the reference we required in the frequency response, which is basically the 0 dB reference. So we need mid-range value. So what is mid-range value we will discuss. So mid-range gain is generally assigned the 0 dB and other all gains are relative to the mid-range. So what is this mid-range? The mid-range is basically the maximum gain that occurs between the lower and the upper critical frequency, which is known as the mid-range frequency region. So we need to get the lower critical frequency and the upper critical frequency, and then only we will get what is the maximum gain in between it. So what is this cutoff frequency or the critical frequency, the two names that we take. So these are basically the frequency where the output power basically drop to half, that is minus 3 dB, and the voltage gain is 70.7% of the mid-range value. Let us try to understand this with the help of frequency response curve. So if you see this 0 dB, which is the reference, this is the maximum value of the voltage gain. This is the mid-range. Now, if the voltage gain falls to 70.7% of the maximum, then we are talking about minus 3 dB. If it is falling to 50% of the maximum, then we are talking about minus 6 dB. So this way we are going in the minus dB frequency response or the gain, and 0 dB is basically the reference from where we are measuring. So when we measure the power, the unit we take is in dBm. So power measurement in dBm, where the reference we take generally 1 milliwatt, and the power which is in dBm is given by 10 log. So this is the actual power divided by 1 milliwatt. So let us understand this voltage gain AV with respect to the decibel value. So if we talk about the 0 dB, so 0 dB when we talk about, this is corresponding to the voltage gain of 1, because 20 log of 1 will give you 0 dB. So this is what our reference we have. Now this side we have the negative value where we are taking minus 3 dB, minus 6 dB and so on. And this side we have the plus dB. So we have the voltage gain, if it is in decibel, then that is corresponding to the negative dB. And if the voltage gain is positive number, then we are talking about the decibel, which is positive. So we take the 0 dB as reference, voltage gain being 1. Same we talk about the power in dBm. So if we talk about the 0 dBm, that is corresponding to 1 milliwatt. And when we talk about the negative value of dBm, we are getting in decimal. But when we talk about the positive dBm, we are getting the positive value of the milliwatt. So this is the voltage and the power gain measurement. Now we talk about the low frequency response first, taking the example of the BJT amplifiers. So there will be 3 high pass RC network, which will be affecting the low frequency gain. So you will be having the input circuit, output circuit, and the bypass part of the RC network. So the network will be RC circuit. So if you see this circuit, this is the BJT circuit or the amplifier circuit. You have the input, output, and the bypass. So input, if you talk about, then we are having basically the capacitor C1 and the input resistances R1 and R2, which is connected in the voltage divider. If you talk about the output part, we have C3 and the output resistance. So this is what you have, the output part. And the bypass capacitor is basically this C2. If we try to simplify this network and try to put it to find the low frequency response in the form of AC equivalent circuit, then we try to see the circuit from this end. This is the input circuit. We try to find the circuit from this end, from the load circuit, that is output circuit. And when we see throughout the emitter, we are getting the bypass. So each circuit has lower critical frequency CL. So when we talk about the CL, it is a critical frequency CL. The lower critical frequency in the input side, when we talk about, so input critical frequency is given by 1 by 2 pi R in into C1. So if we see the circuit for the input side, so input capacitor is C1 and there is a resistor which is forming because of R1 parallel with R2 and R in base. These three capacitors will form the parallel combination and form the total R in value. So if we draw the Bode plot, that is the frequency response of the input RC circuit. So this is the magnitude circuit and this is the phase circuit. So phase response. So we get the response as the roll off minus 20 decibel per decade below the FCL value. So this is what you have, the critical frequency region, and then you have the frequency response which is falling or rolling up by minus 20 decibel per decade. And the phase shifting you can obtain with theta, which is equal to 10 inverse of, you have the value of XC, which is capacitive reactance, and then you have the input resistance. So this is what you have, the phase response at 0 degree. If we talk about the 0 degree, here you have the mid range. 45 degree if we talk about, then here you have the critical frequency, and 90 degree if you talk about, the frequency will be tending to 0. So this is the magnitude and the phase of the input RC circuit when we talk about the BJT part. When we talk about the output RC network for the BJT, the formula for R critical frequency is 1 by 2 pi. Now here you have the capacitors RC and RL. So this is your collector capacitor and the load capacitor. These two are in series, multiplied with C3, that is you have the output capacitor C3. So the development of this equivalent low frequency output RC circuit, we can check the BJT can be replaced with a current source. So this is the dependent current source in parallel with the collector resistor. And when we apply these two in source transformation, we get a voltage source. So if a current source is in parallel with a resistor, we can convert that with a voltage source in series with the resistor. So voltage source in series with the same collector resistor, and the C3 will come here. So this is the simplified equivalent low frequency output RC circuit of the BJT. And the bypass circuit, if we talk about, so here the emitter part, if we see the bypass circuit, here you have 1 by 2 pi, which is the critical frequency of the bypass. And here we need to compute the Thevenin's part of the resistor, which is parallel with the emitter resistor, and multiplied with C2, because C2 is what you have at the bypass. So you apply the Thevenin's theorem here in the circuit. I'm not going with the derivation. So Thevenin resistor will come this one, which is Re dash plus R Thevenin by the beta. Beta is the voltage gain, and divided with Re. So this is the gain. And you have the swamping resistor, which we have discussed in the previous lectures. RE1, this will reduce the effect of C2. So we need to reduce the effect of C2. Then we can put it the swamping register in parallel with the capacitor. Now we discuss the BJT. Let us discuss the FET amplifiers. Same in the low frequency response. So you will have two high pass RC circuit. Previously in BJT you have three high pass circuit. One was the input, second output, third bypass. But here you have two high pass RC network. One is the input, another is the output. So this is the circuit of zero biased MOSFET amplifier. So here if you can see the MOSFET you have, and this is your input and this is your output. So the critical frequency at the input is basically 1 by 2 pi R in C1, similar to the BJT case. And the output you have where the register is basically the drain register plus the load register. So that's the difference in terms of the BJT. But the circuit is one and the same. So the input RC circuit and the output RC circuit of the FET amplifiers we can obtain, and the critical frequency we can obtain it. Now we have discussed the low frequency. We will go with the high frequency. First we will take the BJT amplifiers. So in the high frequency, the internal capacitances will be dominating as we have discussed earlier. So the base to emitter and base to collector will be dominating. We'll apply the Miller's theorem as discussed to split this base to collector into input-output capacitances. So this is our circuit what you have, the capacitively coupled amplifier, and the high frequency equivalent circuit using the internal capacitance, base to collector and base to emitter we have. This part R1, R2, which is the voltage divider, we have here R1 parallel to R2, and the collector register and the load register we have parallel here as the output circuit. So this is the high frequency equivalent circuit. We will apply the Miller's theorem, and from this circuit we will get this circuit where the input capacitance of the Miller and the output capacitance of the Miller, we have to add it in the input and output part of the high frequency equivalent circuit. Now once we have done that, the two low pass RC network, which is the input and the output, will be the total part of the input capacitance, and the Miller will be equal to CBC. And in the input side, we have base to emitter and input capacitance of the Miller. So previous circuit, whatever we have, we try to simplify it. And here you can see these two capacitors will be in series. So CBE plus Cin, that will give you the input side. And the output capacitor will be only the CBC side. So the high frequency input RC circuit for the FET, we can obtain it with respect to Miller to reduce the circuit in a much simpler format. So this is the output RC network. In the high frequency, we have the output Miller part here, C output Miller we have introduced. So the C output Miller, which is present in the output circuit, defines the high frequency FET output RC network. Now, what is the critical frequency of the upper region in the BJT case? So that will be equal to 1 by 2 pi. This is the R in total, C in total. Okay. So that is the input RC circuit. Output RC circuit, we have RC multiplied with C output Miller. Phase shifting, if we see, the output will be lagging the input up to the 90 degree. This will be the upper critical frequency. In terms of the FET, the high frequency response, you need to consider the internal capacitances, gate to source, gate to drain, drain to source, which will be dominating. In the data sheet, it will be mentioned that the gate to drain is equal to RSS, reverse saturation characteristic. Gate to source is the input SS minus the RSS. The CDS is output SS minus the reverse SS. So Miller's theorem will be there to apply to get the CGD capacitor, gate to drain. So this is the total development of the equivalent high frequency circuit of the FET. So this is the junction field effect transistor amplifier in the normal part. We get the high frequency equivalent circuit. So the internal capacitances plays a very important role here, which will be dominating gate to drain, gate to source and drain to source. We apply the Miller's theorem and get the input capacitor and the output capacitor, and we try to simplify this to get the input RC circuit and the output RC circuit to find the total capacitor in the input and the output part of the circuit. So from that, we can find out the critical frequency in the input and the critical frequency in the output circuit as the formula 1 by 2 pi RS C in total, where C in total is nothing but gate to source plus the input of the Miller. In the output, we have 1 by 2 pi RD and the output capacitance of the Miller, which is approximately equal to the gate to drain only as the capacitor. So the Bode plot of the high frequency response, if we see, so we have basically the upper CU, that is the upper critical frequency in the input characteristic and upper critical frequency in the output characteristic, and the voltage gain mid-range. So you will have here flat 0, then you have a minus 20 decibel per decade falling up to upper, and then it will be falling with minus 40 decibel per decade. The frequency response in the phase, so upper cutoff or the upper input cutoff frequency will give you the minus 3 dB here. So this is the phase response of the high frequency of the FET. Now we have seen the low frequency and the high frequency. So the total frequency response is basically the combination of the low frequency and the high frequency response. The dominating critical frequency we need to determine in the highest and the lowest, which is in the highest lower critical frequency FCL, which is dominating, and the lowest upper critical frequency, which is dominating, and then we can get the bandwidth. So bandwidth is basically the difference of the upper critical frequency and the lower critical frequency in the dominating region. So this is basically the total amplifier frequency response. This is the generalized ideal case response curve. So you can see this is the lower part and this is the upper part of the critical frequency. So first it will increase minus 20 decibel, then 40 decibel, and then it will reach to the maximum. It will settle down and then it will fall again. So that is the general case. And the response curve illustrating the bandwidth, which is, this is the dominating part, this part. So here the difference between the upper and the lower will give you the bandwidth. If we do not have this FCL part, this part is not there, then the curve will start directly from here and then fall. So this will be your bandwidth. So if FCL is equal to 0, then we have this response of the frequency. We have discussed low, mid and high frequency region. Now we will discuss the gain bandwidth product. So for a given transistor, the product of the voltage gain in the mid frequency region and the bandwidth is basically a constant Ft, which is the gain bandwidth product. So gain bandwidth product Ft is unity gain frequency when the gain is equal to 1. And this is the constant for a given transistor. Let us take an example. If the voltage gain is 50 in the mid frequency region, then if the constant is 175 megahertz, which is the gain bandwidth product, we can find out what is the bandwidth. So bandwidth is nothing but the Ft value divided by the voltage gain, which comes to be 3.5 megahertz. So 3.5 megahertz is the bandwidth, which is the difference between the upper frequency minus lower frequency in the dominating region. If we talk about the multi-stage amplifiers, then so many amplifiers are connected together, that is a multi-stage amplifiers. There the different critical frequency you can have, or each will have identical stages. So if you have the different critical frequency, then overall which is dominating in the any stage, that you need to consider. So FCL value and FCU value, that is the lower and the upper critical frequency of any particular stage that is dominating, that we need to take into consideration. If it is identical, that all the stages have same value and there are n number of stages, then we can use the formula to find the lower and the upper critical frequency dominating using this formula. So for any stage, we need to find the critical frequency dominating divided by under root of 2 to the power 1 n minus 1, where n is the number of stages. The upper critical frequency is FCU dome. This is for one stage multiplied with certain factor, that is square root of 2 to the power 1 by n minus 1. So here in the lower we are dividing, here in the upper we will be multiplying with the same factor. We have understood the lower, medium and high frequency region for single stage as well as multi-stage. But the question is, how do you measure these frequency response of the amplifier? So in order to measure the frequency response, you need equipment, which is the function generator and the oscilloscope. Two important equipment that you need it. Function generator will be used for giving the signal. So input source you will be giving using the function generator, and oscilloscope you will be measuring the both the input as well as output signal. And the procedure that you need to follow is you need to set the mid-range frequency by adjusting the input voltage to 1 volt as the output. So input which is given with respect to function generator, you need to adjust to 1 volt and set the mid-range frequency. Decrease the frequency to so that the output is 70.7% of the mid-range frequency, and determine the critical frequency of the lower. Increase the frequency to get the 70.7% of the mid frequency to determine the upper critical frequency. So once you get the lower upper critical frequency, you can easily determine the frequency response. So your frequency response will be like this. So you have the critical frequency. So this is your lower, this is your upper, and this is your mid-range. So here you have the mid-range frequency. So this is the general procedure that can be followed in the laboratory to find the amplifier frequency response. So we need function generator, we need oscilloscope, and the amplifier circuit that you have. This function generator will be given the input signal, which is 1 volt. We have to set it, and we need to measure the lower and the upper critical frequency by increasing the mid-range from 70.7% plus to 70.7% minus, and measure the input and the output for different frequency. So here you can see 6.67 for this example kilohertz. This is the mid-range frequency at 1 volt, and 125 hertz, which is the lower critical frequency when you are getting 70.7% of the voltage gain. Whereas the upper critical frequency is 500 kilohertz, which is the frequency response when you have 70.7% of the mid frequency region. Then once you get this, you can easily obtain the response of lower and the upper critical frequency, and this is what you have, the mid frequency region. You will get the frequency response. So let us summarize what we have discussed. We have discussed the amplified response varies with frequency due to the capacitive effect. So due to the presence of input capacitor, output capacitor, and the bypass capacitor, we have the variation in the low frequency and the high frequency. Low frequency, we have coupling and the bypass capacitor, which will reduce the gain. High frequency dominating factor will be the internal transistor capacitance, which will reduce the gain. Bandwidth is determined by the finding the dominant critical frequency, the lower and the upper. And multi-stage amplifier have narrower bandwidth than single stage. So if you have the single stage, you have broader bandwidth. If you have multi-stage amplifier, you have narrower bandwidth because of the factor 2 to the power 1 by n minus 1, which is the square root. So this complete our discussion on frequency response of amplifiers. In the previous lectures, we have discussed more detail about the mid-frequency region where we have sought the capacitors and done the response analysis. Here we have done the detail analysis. So see you in the next lecture. Thank you for now.